Hello everyone. In this video I am going to explain the frequency domain analysis of any discrete LTI systems. Basically we are going to use the discrete time Fourier transform in any discrete time LTI systems to get the frequency response of the systems. So let's start. So frequency response analysis of discrete time system. Now, as we know, the output y of n of any discrete LTI system for known impulse response can be obtained by using the convolution sum as this. So summation over k is equal to say minus infinity to infinity in general. H of k, since convolution is commutative, we can write h of k first, then x of n minus k, or x of k into h of n minus k, same thing, because convolution is commutative. Where it is h of n is your impulse response of the system. Now let us assume that the input x of n is a complex exponential function of the form e to the power j omega n, where omega is any frequency. Now if we apply this x of n is equal to e to the power j omega n as an input to the system, then the output can be calculated from the above convolution sum as this. So it will be k minus infinity to infinity h of k. Instead of x of n minus k, now it will be e to the power j omega n minus k. Alright, so then if we just simplify it, it will be like, since this summation over k, so this e to the power j omega n, that can be kept outside the summation, so it will be here e to the power j omega n summation over k minus infinity to infinity, summation over k minus infinity to infinity h of k into e to the power minus j omega k. Now look at this term. So this term is nothing but here the definition of the discrete time Fourier transform of h of k. So what we can write? We can write here h of capital H of e to the power j omega, which is the dtft of h of k. So we can write it like e to the power j omega n into h of e to the power j omega. So this is called, this h of e to the power j omega is called the frequency response of the system. Okay, frequency response of the system, and this is the nothing but the input, exactly the input. So the output is input only. If the input is your complex exponential, output is input only. The difference is the input get multiplied by a complex valued function h of e to the power j omega, which is known as the frequency response of the system. Now this function h of e to the power j omega, which is nothing but here this k is equal to minus infinity to infinity h of k into e to the power minus j omega n, or j omega k actually, or in case if you write here and h of n e to the power minus j omega n, then it will be summation over n is equal to minus infinity to infinity, the same thing only. So therefore this function h of e to the power j omega, it exists if the impulse response, because this h of k is nothing but the impulse response of the systems, this impulse response is absolutely summable, as already we discussed in my previous video where I have discussed this dtft. So we have found that the existence of the dtft, or the convergence of dtft, is basically the primarily the necessary condition is that the signal h of n or x of n, whatever it should be, absolutely summable. Now since we have derived this h of e to the power j omega as equal to k minus infinity to infinity, this thing, so this is nothing but the definition of the dtft. So this is exist only when this is, that means h sub k is absolutely summable. Okay, so we can see from this y of n is equal to e to the power j omega and h sub e to the power j omega, from which we can see that for an input x of n which is equal to e to the power j omega n, the output of this LTI system, LTI discrete time system, is also an exponential signal, that the same signal, okay, but is being multiplied by a factor h sub e to the power j omega. So this is the same quantity of the same frequency omega, but get multiplied by this particular term h sub e to the power j omega. So this type of signals that produces, so what type of signal? This type of e to the power j omega, and this type of signal which produces a response. This is the response which produces the response, which is simply differs from the input signal. This is being output y of n is being differed by the input multiplied by a complex constant. This is a complex quantity, complex constant. If we take the magnitude, it will be a complex constant. Okay, are known as the eigenfunctions. So what I mean to say is this type of signal, okay, that produces a response which is differ from the input by input signal by a complex constant. This is complex constant, are known as the eigenfunction. Okay, known as the eigenfunction. And the values of the complex constant, whatever be the values of this complex constant h sub e to the power j omega, evaluated at the frequency omega, that is the frequency of the input signal, is known as eigenvalue of the system. Okay, so this quantity h sub e to the power j omega is also called the frequency response of the system. Now from this we can find that the frequency response of a discrete time system is nothing but the discrete time Fourier transform of the impulse response of the system. Now, since the frequency response h sub e to the power j omega is a complex valued function, it can be expressed as in a polar form, something like this. So this h sub e to the power j omega already we discussed in Fourier DTFT. So this h sub e to the power j omega is a complex quantity, so it can be represented in a polar form like this: magnitude of e to the power j omega and e to the power j theta omega, where j theta omega, this magnitude, this is the magnitude, okay, magnitude response of the system, so it is the magnitude, and this theta omega is the phase. Okay, this theta omega is the phase response. Okay, magnitude response and the phase response. So this theta omega is actually nothing but your angle phase part of the h sub e to the power j omega. Okay, so we will get from the frequency response of the system, LTI system, so what we will get? We will get the magnitude response as well as the phase response of the system. Okay, now from the properties of the DTFT, we know that the magnitude of DTFT is always event symmetric. That means a magnitude of h sub e to the power j omega is equal to magnitude of h sub e to the power minus j omega. Okay, that means your magnitude is event symmetric and the phase is odd symmetric. That is theta omega is equal to minus theta minus omega. Okay, that is odd symmetric. That already discussed in my video lecture on the DTFT. Okay. Also, from the DTFT already we talked about this. DTFT is periodic. That means this, in this case here, the frequency response h of e to the power j omega, which is nothing but the DTFT, discrete time Fourier transform of the impulse response, which is the magnitude is even symmetric, phase is your odd symmetric, and this h of e to the power j omega is periodic over period twice pi. That is any integer multiple of twice pi. That is k into twice pi. Now, since your magnitude is even symmetric and phase is your odd symmetric, and also it is periodic over the period twice pi, so we can plot or we can evaluate the spectrum. That means the response, frequency response h of e to the power j omega only for 0 to pi is sufficient. Okay, because minus pi to 0 will be same, magnitude will be same because of the even symmetric, and the phase will be odd symmetric, same only, just the odd symmetric. So we need to evaluate only for the 0 to pi, or equivalently minus pi to pi, same thing only, but we need to evaluate only 0 to pi. Okay. Now let us consider a first order system. So how we will define a first order system in discrete time? So can be the first order system in discrete time can be defined as y of n, say, is equal to, or say, minus a y of n minus 1 plus is equal to x of n, or it is y of n is equal to x of n plus some constant a into y of n minus 1. This is the first order the discrete time systems, where your x of n is the input and y of n is the output. Now if we take the Fourier transform DTFT both side of this equation, then what we will get? Directly you just take DTFT of this equation both side. So it will be your y of e to the power j omega, then minus a is arbitrary constant, so it will be there only. Y of n minus 1 is, according to the shifting property, it will be minus j omega into y of e to the power j omega is equal to x of e to the power j omega. Okay, then you make this y of e to the power j omega common, so then it will be 1 minus a e to the power minus j omega is equal to x of e to the power j omega. So from this, y of e to the power j omega divided by x of e to the power j omega is equal to 1 divided by 1 minus a to the power a into e to the power minus j omega. So this is the DTFT of the output divided by DTFT of the input. So it is nothing but the transfer function. That is, we can define it as h of e to the power j omega, which is the frequency response 1 upon 1 minus a e to the power j minus j omega. Okay, so from this, what we will get? This is the frequency response, and already we have come across that this h of e to the power j omega, which is the frequency response, is nothing but the DTFT of the impulse response. Now from which we can calculate the impulse response as the inverse the Fourier transform or inverse DTFT of your h of e to the power j omega. Okay, that means here it is 1 by 1 minus a e to the power minus j omega. Okay, and by definition we easily can find that this is a to the power n un, because if we look at the a to the power n un, the DTFT of a to the power n un is nothing but 1 by 1 minus a e to the power minus j omega. So if we do the inverse of this, then it is nothing but a to the power n u of n. Okay, so finally you see from the frequency response we can get back the impulse response of the systems. Okay, so the frequency response of the first order system is this. Okay, and from which we can obtain the impulse response of the first order system as this. Okay, now this h of e to the power j omega is called the frequency response of the LTI systems, and the h of n is the impulse response of the systems. Okay, further this h of e to the power j omega we can write like further this h of e to the power j omega, which is 1 by 1 minus a into e to the power minus j omega, and we know that e to the power minus j omega is cos of omega minus j sin of omega, so it will be minus a cos of omega then plus a j sin of omega. So from which we can see that this part is the real part and a into sin of omega is the imaginary part. So if we then calculate the magnitude of h of e to the power j omega, it will be 1 upon square root 1 minus a cos of omega square plus a sin of omega square, and from which it will be your square root 1 minus twice a cos of omega plus a square cos of omega, a square sin of omega is 1, so it is a square. Okay, so it is the magnitude response of the frequency response h of e to the power j omega. Similarly, the phase response theta omega, which is the angle of the h complex quantity h of e to the power j omega, it will be tan inverse of b by a. Okay, so again tan inverse of 1 is, because it is 1 upon, no, 1 upon, so tan inverse of b by a, so here it will be 0, that is 0 by 1, that means it is 0, then minus tan inverse of a sin of omega divided by 1 minus a cos of omega, so it is, finally it will be minus tan inverse of a sin of omega divided by 1 minus a cos of omega. Okay, now based on these two, that is magnitude is this and phase is this, based on these two we can now plot the magnitude spectrum and the phase spectrum for the given first order system. So as I mentioned, this magnitude is even symmetric and our phase is odd symmetric, so we can draw only for, that means we can evaluate only for 0 to pi. That means for different values of omega starting from 0 to pi, we can evaluate this magnitude and phase. Okay, and then plot it. So it will be look like this. So your magnitude response, this is your magnitude response, magnitude of h of e to the power j omega. Okay, and this way it is omega. So if we evaluate this function, if we evaluate this this 1 upon 1 minus 2a cos of omega plus a square, say for any arbitrary constant, let us consider say a is equal to some say constant, say for example 0.8. Okay, so for 0.8 a is equal to 0.8. Now if we evaluate for different omega starting from 0, say 0, if it is 0, then it is cos of 0 is 1, then 1, cos of 0 is 1, so it is 2 into 0.8 into 1 minus 0.8 square, like that you evaluate for different values of say omega, say 0, pi by 2 pi, and similarly theta omega also, then you'll get this type of curve. Okay, this type of curve, and as you see, sorry, this will be somewhere, this part will be somewhere here, because this is pi only, so it will be like this way, like this way. Okay, this is your pi. So from this and this part, if you see, both are same only, because it is even symmetric. Okay, similarly the phase factor, if we evaluate, then it will be like this. So you need to evaluate from 0 to pi, because it is odd symmetric, so it will be just like this from pi to 2 pi. Okay, because of the odd symmetric. And similarly this side also you will get the same curve. Okay, so this is how we go for the magnitude and the phase response out of the frequency response of the discrete time LTI system. Similarly, you can go for the frequency response analysis of your discrete time in second order system. So your second order systems is of the type y of n minus say some constant a1 y of n minus 1 minus a2 y of n minus 2, because it is second order, and is equal to x of n. Okay, this is your second order feedback system. So where again you can apply directly the DTFT both sides. So it will be your y of e to the power j omega minus a1 e to the power minus j omega into y of e to the power j omega, then minus a2 e to the power minus twice j omega into y of e to the power j omega is equal to x of e to the power j omega, and from that you can calculate y of e to the power j omega divided by x of e to the power j omega, and accordingly you can go for the magnitude and phase response. Okay. Next is the transfer function. Already I talked about the transfer function from the DTFT, that is from the frequency response. Okay, so this transfer function, already I talked about this h of e to the power j omega, which is y of e to the power j omega divided by x of e to the power j omega, is the transfer function, and which is nothing but the Fourier transform of the impulse response of the h of n. And h of e to the power j omega already is equal to your y of e to the power j omega divided by x of e to the power j omega. So this h of e to the power j omega is your DTFT of the impulse response of the systems, x of e to the power j omega is the DTFT of the input, and y of e to the power j omega is the DTFT of output. So let me derive this in a slightly different way. Okay, slightly different way. Now, for any arbitrary input x of n, we can represent that x of n based on the IDTFT formula. So by the definition, 1 by 2 pi, 0 to pi, or minus pi to pi, or 0 to 2 pi. Sorry, it is minus pi to pi or 0 to 2 pi, x of e to the power j omega into e to the power plus j omega n d omega. So this is nothing but the IDTFT formula, that is inverse DTFT formula. So for any arbitrary input x of n, we can represent that x of n of this form, where your x of e to the power j omega is nothing but the DTFT of x of n, which is defined as summation over, that means this x of e to the power j omega, which is defined as summation over n minus infinity to infinity x of n e to the power minus j omega n. Okay, now already we have derived this y of n for any discrete LTI system, y of n for the input e to the power j omega n, we obtain it as h of e to the power j omega. Okay, so where x of n is e to the power j omega n. Okay, now we can simply write the y of n also in terms of the IDTFT formula. So that is 1 by 2 pi minus pi to pi y of e to the power j omega. Okay, y of e to the power j omega into e to the power j omega, that means this y of e to the power j omega into e to the power j omega n d omega. Now, as you can see, this y of n, which is e to the power j omega n into e to the power h of e to the power j omega. Now from this what we can write, y of n is equal to this e to the power j omega n is nothing but your x of n, that is, it is just as an input x of n. Okay, so for this because this is your input x of n. For this you just write the IDFT formula, which is 1 by 2 pi minus pi 2 pi x of e to the power j omega into e to the power j omega n d omega, and d omega will write later, into this part h of e to the power j omega d omega. Okay, now if you see, this is directly for the y of n as per the inverse DTFT, 1 by 2 pi minus pi 2 pi y of e to the power j omega into e to the power j omega and d omega, and this is from this where it is e to the power j omega n, nothing but the x of n, for which I have written the IDFT up till this, and this h of e to the power j omega. Now compare these two. Okay, you just compare these two. What is there instead of y of e to the power j omega? Instead of y of e to the power j omega, it is your x of e to the power j omega into h of e to the power j omega. So you just compare these two equations. If we compare these two equations, because both are yn, so if we compare both these equations, so we'll find y of e to the power j omega is equal to x of e to the power j omega into h of e to the power j omega. So where therefore h of e to the power j omega will be your y of e to the power j omega divided by x of e to the power j omega. So this already derived, but this way also we can derive. So this is what we call the frequency response of the systems, also the transfer function of the systems, which is nothing. If we say the frequency response of the system, that is nothing but the DTFT of the impulse response. Then if we say it in as a transfer function, which is nothing but the DTFT of the output divided by the DTFT of the input. Now another point. So already we have discussed that if my x of n, so I am now considering x1 of n. So if my input x of n is e to the power j omega n, then what will be my output? So let it be y of n, y1 of n. So my output will be the same input only, e to the power j omega n, but along with h of e to the power j omega. Okay, h of e to the power j omega. So now if we take in terms of magnitude, then it will be your magnitude of this. If I take the magnitude of this, it will be equal to magnitude of h of e to the power j omega, because magnitude of e to the power anything is 1. So if we take the magnitude of this, it will be your magnitude of h of e to the power j omega into in the polar form I am writing, actually in the polar form. So magnitude of this into e to the power j theta omega. Okay, so I am writing the polar form of this here, and into e to the power j omega n. Okay, now suppose this e to the power j omega n x1 of n, which is also suppose it is being multiplied by some constant a. So since the Fourier transform is linear, that linear weight will be here also, okay, and here also. Getting? Similarly, that already we discussed. Similarly, if suppose I am considering another one, x2 of n as a minus j omega, that is suppose a into e to the power minus j omega n. Okay, if it is e to the power minus j omega n, so then what will be the output? Like this, y2 of n, it will be a, because it is minus, so here it will be a e to the power minus j omega, right? Then e to the power minus j theta omega, and e to the power minus j omega n. Okay, right? Now, as already we know that the DTFT is linear, so what I did is first I have evaluated the DTFT of x1, which is y1, same next x2, then y2. So if I now add this y2 and the y1 and the y. Sorry, this is not DTFT, this is just the output of the systems. Okay, y1 is the output, already discussed, and y2 is also the output for the input x2. Here y1 is the output for the input x1. Okay, now as we know, if we suppose x of n, if I edit up x1n plus x2 of n, okay, if I edit up, then what will get? It will be a to the power j omega n plus a to the power minus j omega n. So what I can write it as? We can write it as a twice a cos of omega n. Okay, because this cos is nothing but cos of theta is e to the power j theta plus e to the power minus j theta by 2. So it will be twice a cos of omega n. Now instead of plus, suppose I will make it minus. If I make it minus, then it will be twice a j sine of omega n. Okay, because sine of omega n is e to the power j omega n minus e to the power minus j omega n divided by twice j. So it will be twice a j sine of omega n. Okay, now from this, because it is nothing but these two, so if my input x of n is this, then what will be the y n then? Simply you add it up. Okay, both of this, that means this and this. Okay, so what will be your y of n? There will be 1 by 2j term will be there because of this 2j. So it will be for y1, this is your y1, so therefore it will be a by your a by twice j h of a to the power a by 2j I can make common because both there is a. So e to the power h of e to the power j omega magnitude into e to the power j theta omega into e to the power j omega n. Okay, this is for y1. Then minus again a by 2j. So a by 2j I made common already. H of e to the power minus j omega e to the power minus j theta omega into e to the power minus j omega n. Okay. So here also we can make a h of e to the power j omega common because magnitude is even symmetric. Okay, since magnitude is even symmetric, that means this and this is equal, so we can make it like a by 2j h of, okay, 2j I'll input, make it inside, so a into magnitude of h of e to the power j omega. Okay, so it will be your e to the power j theta omega e to the power j omega n, then minus e to the power minus j theta omega e to the power minus j omega n divided by twice j. So hope you understood this part. Then we can write this for h of e to the power j omega I make common because this and this are same only because it is even symmetric. Then we'll left behind this, and this part is nothing but this part is this, so 2j I'll make it inside, so it is sine of omega n plus theta omega. So as you can see, when my input was x of n is equal to a e to the power j omega, output is a h of e to the power j omega into e to the power j theta omega into e to the power j omega n. Same way, if minus a into e to the power minus j omega n, then it is a h of e to the power minus j omega e to the power minus j theta omega into e to the power minus j omega. Similarly, if my input is sine, say twice A or simply A sine, because 2j will be anyway that side. So A sine, then we will get A h sub e to the power j omega sine of omega n plus theta omega. Okay. So what does it mean? If it means if the input to the LTI discrete time system or LTI system is a sinusoidal signal, because this is for the sine. So if the input to the LTI system is a sinusoidal signal of frequency say omega, then the output is also a sinusoidal, as you can see. So the output is also a sinusoidal signal of the same frequency. Okay, of the same frequency, but it is lagging by a phase angle of theta. So you see it is sine of omega n plus theta omega. So what does it mean? It is same sign, but it is being lagged or lagging behind by a phase angle of theta omega. Okay, and this part it is just the magnitude, so it will be a constant. So this is being multiplied with this, so together this will represent the amplitude of this sign. So it is slightly amplitude get modified, but more important is it is the same sign of the same frequency omega, but phase it is being lagged by phase angle theta omega. And the same further can be written like this. We can further write this sine part as you just make omega common, so it will be n plus theta omega by omega. Okay, so you can write like this. Now see, this is the output yn for the input xn a sine of omega n. A sine of omega n, right? So this is the output for the input a sine of omega n. Now if you compare this output with respect to the omega n, forget about this. This is just the magnitude part. Okay, main part is this. So if we compare this sine, this was omega n, this is also sine, but you see this n. Here it was n, now it is n plus omega, theta omega by omega. That means there the output y of n has a time delay. It may be delay or advance, whatever. Finally, it is a time delay of theta omega by. So there is a time delay at the output. There is a time delay which is theta omega by omega. Okay, when we compared this output with respect to the input. Now in certain application, this time delay of the signal passing through a filter, okay, any kind of filter of more significance than the phase shift. Okay, this time delay is more significant than that of the phase shift. Okay, so in terms of this input output, we can say it is the time delay. But as we look at, this is nothing but the term, the delay term is the theta omega by omega. So which is the your phase, right? Theta omega is nothing but the phase part. So that is why it is also called. And since I am talking about it as a delay, so you just put a minus over here. So minus theta omega by omega. And since it is theta, that is a phase, so it is also called the phase delay. So it is denoted as tau p. So this is the phase delay. This is very important while analyzing the discrete time LTI system. Generally, the filter we'll talk about later. Okay. Now, say if the input signal contain many frequencies, and those are supposed not harmonically related also. That means when the input signal containing many frequencies that are not harmonically related and which is being processed by your LTI system, in general we call it as a filter, okay, then each component in the signal undergoes different phase delay. Okay, if the signal, that means input signal x of n, contain many frequency component, okay, which are not harmonically related, then each component in the signal undergoes, that is in the output, each component of the signal undergoes different phase delay. Okay, so when there is a different phase delay in the same systems at the output, then it is better to represent this phase delay in terms of group delay. Okay, group delay, which is nothing but your dd omega of, that is first order differentiation of, that means actually it is dd omega of theta omega. So dd omega of theta omega minus, and it is denoted as tau z. Okay, so your tau z, which is the group delay, d theta omega by d omega. Okay, which is the group delay. So the group delay at a given frequency represents the slope of the tangent line at the particular frequency if you draw it. Okay, for an ideal filter, that is an ideal system, the phase and the group delay are identical, that means same. Okay, so that is all about the phase delay and the group delay. So this phase delay, group delay, these two terms is very important while analyzing the filter. Okay, filter in general, it is an LTI system. Okay, so this is all about the frequency response of an LTI system. So this will be very much applicable while we'll go further the LTI systems, that is nothing but the filter. So we'll study the different FIR and IR filters, so in which this frequency response analysis is very much essential. So in this video what we have seen, we have studied the frequency response analysis of the discrete time system. Okay, so from where we analyze this h of e to the power j omega, h of e to the power j omega is called the frequency response, and when it is a frequency response is nothing but the dtft of the impulse response, so it is a complex quantity, so therefore there will be magnitude and phase. Okay, magnitude is even symmetric, phase is odd symmetric. Then we have seen a first order system, okay, and analyze this frequency response of the first order system, okay, both magnitude and the phase. Then we have analyzed the transfer function of LTI system in terms of the frequency response. Then finally for the group and the phase delay we have done all this stuff. Okay, so finally we have derived the group and the phase delay as the phase delay as minus theta omega by omega, and group delay as dd minus dd omega of theta omega. Okay, hope you understood. For any further query, kindly contact me. Thank you for listening.